My name is Isabella Weiner, and this is my 4-year research project, In Situ Resource Utilization of Martian Regolith for Construction. We are going to go to Mars, and on Mars we're going to need a way to build using what's already available. Having to bring materials from Earth would be expensive and inefficient. Which brings us to In Situ Resource Utilization, which basically just means using the resources already available on Mars, in situ, or in that place. And my suggestion for this is sulfur-concrete. Regular concrete is made using water, cement, and an aggregate. However, water is a valuable resource, and cement isn't even available on Mars. Sulfur concrete, in contrast, is made only using aggregate and sulfur, heated to sulfur's melting point of 115 degrees Celsius and mixed together. Therefore, sulfur concrete is a way to use materials already present on Mars in place of valuable resources. In year 1 of my project, I decided to test the different strength of sulfur concrete with different aggregates found on Mars, such as basalt, conglomerate, sandstone, and the natural soil simulated by a Martian soil simulant provided by NASA. So what I did was I created a series of bars made from each type of aggregate in a 50-50 ratio developed from previous studies. And I tested these using a homemade tensile strength test in which the bars were placed between 2 pieces of wood and a string with a bucket attached was held from it. And sand was poured into this bucket basically until the bars snapped and the weight in the bucket was recorded. So I ended up figuring out that basalt actually made it the strongest out of all the aggregates and concluding that using soil rich in basalt would help make it stronger. So the next year of my project, I had noticed a bit of a chemical reaction that first year. I had seen it bubble when I used a lot of basalt, which has a lot of iron. So I decided to try to add more iron to reinforce the sulfur concrete and make it stronger. Additionally, I decided to improve my method for creating the sulfur concrete. The first year, I used a little ingot mold and a hot plate, which was very difficult to try to get the bars out. So the second year, I switched to an oven and silicone molds to make cubes and thicker bars. These bars I then tested the same way as in the previous year. With the cubes, I managed to get a standardized testing using a universal testing machine at a UCF lab to perform compression testing. And I ended up determining that the sulfur concrete held over 6,000 psi, or pounds per square inch, which is actually the same as Portland concrete. While I didn't see any significant difference from adding the iron, this completely validates sulfur concrete as a building material on Mars instead of regular concrete. So once I established sulfur concrete as a valid building material, the next step was to start thinking about a valid building method of construction. And I decided to focus on additive manufacturing. Additive manufacturing refers to 3D printing material layer by layer, and it's currently being used by certain companies to print concrete houses here on Earth. So I decided to adapt this for sulfur concrete, and I designed a system for additive manufacturing on Mars, or SAMM, in order to 3D print sulfur concrete as a model for future construction of homes on Mars. This is SAMM, composed of an extrusion system, a gantry system, and a control system. Let's take a look at how it was built. So the first stage of creating SAMM was creating a gantry system. The 2 main designs for 3D printers for large-scale structures are a robotic arm, which doesn't have a full range of motion, so isn't as good for creating large-scale structures in one go. So I decided on the gantry system, which has movement in the X, Y, and Z axes, as shown here. That way, it can build up and around in a Cartesian coordinate. So I determined the optimal ratio of aggregate to sulfur for 3D printing sulfur concrete using a slump test, which is a standard construction test to determine workability. Basically, it's poured into a cone, removed, and the slump is measured. So here you can see I modified it using small paper cups. And you can see with the 50-50 ratio that was based on previous studies, based on strength, that totally collapsed, which isn't good. That means it's too liquidy. So here I up the ratio. This is 60% aggregate, 40% sulfur. And in this case, the aggregate is a Martian soil simulant. And you can see there it didn't drop at all, which is called zero sump, which also isn't good. There's actually a very delicate balance between extrudability, being able to actually be forced out of a system, and buildability, the ability to layer. So that's a really delicate balance and really important, which is why I did this testing. So you can see that's an even steeper ratio, really crumbly. So here is a 55-45 ratio, which was in between collapsed and zero slump. And as you can see here, it drops a little bit, but not all the way, which is called true slump, meaning that this is the optimal ratio for 3D printing sulfur concrete. So extrusion testing, I actually had to switch back to the less optimal 50-50 ratio because the thicker 55-45 kept solidifying in the tubing and just getting clogged. So I ended up fixing that by using some hot water run through to help heat up the tubing. And additionally, I ended up powering it with gravity. I had also tried air compression and a manual plunger, but gravity at a steep angle was really the only thing that could get it flowing fast enough so it wouldn't be solidified. And as you can see, it's coming out in a pan here, and I weighed the mass of that pan before and after to calculate efficiency. So this is the integrated system, which is basically just combining the extrusion system and the gantry system, which I had already created. And here you can see that I programmed the nozzle to move around in a 20 by 20 centimeter square. And after each tracing of the square, it moves up just half a centimeter. So here's the first successful print. As you can see here, it actually just comes out in one spot for a little while and forms sort of a puddle. That's actually because the programming was starting a little too late. So you'll see it does start moving eventually, and it does manage to trace that program 20 by 20 centimeter square, which demonstrates that I was able to program the printing of sulfur concrete in this trial, even though it was kind of clumped and it wasn't able to layer up because I was limited on how much I could pour through at a time, simply based on how it would start to solidify in the tube. And this is another print that I did. And this one, I started the programming more on time, so you'll see it does get to do a few different tracings and start to actually layer up. And you can see it is kind of liquidy, and that comes from having to switch to that less optimal ratio. But because I did determine that more optimal ratio, if I had heated tubing, I would be able to use that ratio, and it would be a lot more precise and actually be better for building up actual structures. So in the end, I would definitely use the optimal ratio that I determined. But you can see this does start to build up, and it does demonstrate SAMM's effectiveness at being able to print sulfur concrete. SAMM still has a long way to go, such as by adding heated tubing and a compressed air system to adapt to the Martian conditions. However, eventually we might be able to 3D print sulfur concrete homes on Mars, and even here on Earth, using sulfur waste to be able to produce efficient, resourceful homes.